All right, let's dive into one of the most powerful and, honestly, elegant ideas in programming. It's called backtracking, and it's basically a secret weapon for solving problems that seem impossibly complex. We're going to break down exactly how it works. So here's a question for you. How in the world can one single, simple concept be the key to cracking both a classic chess puzzle and a Sudoku grid? I mean, on the surface, they feel like totally different challenges, right? But it turns out they share this hidden logical structure. And that unifying idea is backtracking. It's not some kind of magic trick. It's just a brilliantly systematic way of searching for a solution. It's this one powerful algorithm that connects these seemingly random, tough puzzles. Okay, so let's actually build out the blueprint. We're going to get right into the nuts and bolts and break down the simple yet incredibly effective logic that makes this whole thing tick. You know, at its core, backtracking is all about building a solution one step at a time. But here's the crucial part. The very instant you realize a path is a dead end, you stop. You just abandon it, turn around, and try a different path. It's all about not wasting a single second on a choice that you know is wrong. The absolute best way to picture this is to think of a giant tree with tons of branches. Every decision you make is like choosing a new branch to walk down. Backtracking is just a really smart, methodical way of exploring that tree to find the right path. And really, this whole complex-sounding process boils down to a super simple three-step mantra. First, you choose a path. Then you explore it, you go deeper. If that path doesn't work out, you unchoose your last decision, that's the backtrack, and you try another one. Choose, explore, unchoose. That simple loop is the engine behind it all. And this is what makes it a total game changer compared to a naive brute force approach. See, brute force would just blindly try every single possibility, walking down every last branch of that tree. Backtracking is way smarter. It intelligently prunes or chops off entire sections of the tree that it knows are dead ends, and that's where all its efficiency comes from. Okay, enough theory. Let's make this real. Our first case study is a classic computer science problem, the n-queens puzzle. This is just the perfect way to see our backtracking blueprint in action. The goal is simple, right? You've got a chessboard of size n by n, and you need to place n queens on it. The only catch? No two queens can threaten each other. So that means no two queens in the same row, column, or diagonal. And you can see that mantra right here. We choose to place a queen. That one move instantly makes a bunch of other squares on the board invalid. So as we explore where to put the next queen, we don't even bother with those spots. And if we get stuck, we unchoose, move that first queen over, and start the process again. Now, the time complexity here, yeah, it can look pretty intimidating. It's O of n factorial, which grows incredibly fast. But because we're doing all that smart pruning, it's actually manageable for reasonably sized boards. And here's a little fun fact for you. While you can't solve it for a 2x2 or 3x3 board, a solution is always possible for any board that's 4x4 or bigger. Kind of cool, right? Okay, so that's a chessboard. What about something totally different, like a number grid? Let's take the exact same logic, that same blueprint, and apply it to a completely different challenge, solving a Sudoku. The mapping from one problem to the other is actually pretty direct. This time, our decision isn't which column to pick, but which empty cell to fill in. And our choice is simply which number from 1 to 9 we're going to try to plug into that cell, as long as it follows the Sudoku rules. But to make a Sudoku solver really fly, we need to add a little secret sauce. It's a trick called a heuristic, specifically the most restricted variable, or MRV. The idea is brilliant. Instead of just picking any old empty cell, you strategically pick the one that has the fewest possible numbers that could legally go there. It's all about failing faster or finding the one obvious move. And you can see right here why this is such a big deal. I mean, why would you start with a cell that could be 7 different numbers, creating 7 new branches to explore? By picking this MRV cell, which only has 2 options, you dramatically slash the amount of work you have to do. It's a huge optimization. So let's put them side by side. The core pattern is identical. The decision is different, the constraints are different, and yeah, the complexity is different. But that underlying engine, choose, explore, unchoose, is exactly the same. It just goes to show you how versatile this whole approach is. Okay, so puzzles are fun, but why does any of this actually matter? Well, because this way of thinking is incredibly valuable in the real world, especially if you ever find yourself in a technical interview. There's a reason interviewers are obsessed with these kinds of problems. They're not just trying to see if you can code a solution. They're testing if you can break a big, messy problem into smaller pieces, define the rules of the game, and think critically about how to find an answer efficiently. So, if you're ever in an interview and you sniff out a backtracking problem, here's your game plan. It's a 4-step framework. 1. Define your state. How are you going to represent the board? 2. State your pruning rules. What makes a move invalid? 3. Justify how you search. Are you using a heuristic like MRV? And 4. Talk about the trade-offs. What's the time and space complexity going to look like? And trust me on this pattern shows up all the time. It's not an accident that it has such a high frequency in interviews. It's a direct signal that it's a fundamental, must-have skill in computer science. So, at the end of the day, here's the big takeaway. Backtracking isn't just a cool trick for solving puzzles like N-Queens or Sudoku. It's a core, fundamental pattern for tackling any problem where you have to search for a solution within a specific set of constraints. And that leaves us with one final thought. Now that you have this blueprint, this mantra of choose, explore, and unchoose, what other problems out there that once seemed impossible, maybe in scheduling or logistics or even game design, can you now see a clear path to solving?